When I say the universe feels too precise to be accidental, I am not making a mystical claim. I am describing a pattern that appears again and again when we study the cosmos with physics. We measure numbers that control how matter behaves, how spacetime curves, how the universe expands. And many of those numbers turn out to sit in very narrow ranges where complex structures like stars, galaxies, and chemistry can exist. My goal here is not to argue that this implies any particular meaning. My goal is to show you what those numbers are, how we know them, and why they make many cosmologists pause and say, "That is surprisingly specific." I want to start with something very basic. The idea that the universe is governed by a few simple laws that seem to work everywhere we look. When we observe a galaxy billions of light years away, the same laws of gravity, electromagnetism, and quantum mechanics describe what we see. The spectrum of light from a distant galaxy shows the same atomic fingerprints that we measure in a lab on Earth. Hydrogen absorbs and emits light at the same wavelengths. The electron has the same charge. The speed of light is the same. This uniformity is not obvious a priori. It is an empirical fact. We know it because we can compare data. We measure spectral lines, redshifts, orbital motions, and they all fit one consistent framework. Now, inside that framework, a few parameters stand out. One is the strength of gravity, encoded in Newton's constant g, or in general relativity in the way mass and energy curve spacetime. Another is the strength of the electromagnetic force. Another is the mass of the proton. Another is the cosmological constant, or dark energy density, that drives the accelerated expansion of the universe. These are not numbers we derive from deeper theory today. We measure them. They are inputs, not outputs. And when we ask, what if they were slightly different, we find that small changes could lead to a universe that looks radically different from ours. Let me connect this to dark energy and cosmic expansion, because that is where the precision feels especially striking. Dark energy is our name for the observed fact that the expansion of the universe is accelerating. We infer this from several independent lines of evidence. The first strong evidence came from Type 1a supernovae in the late 1990s. These are exploding white dwarf stars that, under certain conditions, have a fairly uniform peakness. That makes them standardizable candles. By measuring how bright they appear, we estimate how far away they are. By measuring their redshift, we estimate how fast the universe was expanding when the light was emitted. When teams plotted distance versus redshift for many supernovae, they found that distant supernovae were dimmer than expected in a universe that was slowing down under gravity alone. The data fit better if the expansion had started to speed up a few billion years ago. This acceleration can be described in Einstein's equations of general relativity by adding a term called the cosmological constant, often denoted by the Greek letter lambda. In modern language, this lambda behaves like a constant energy density of empty space. We call that dark energy. When we combine supernova data with measurements of the cosmic microwave background and large-scale structure, we infer that about 70% of the total energy density of the universe today is in this dark energy component. The rest is mostly dark matter and a small fraction of ordinary matter. The number that describes the dark energy density is extremely small in natural units. If we try to estimate the energy of the vacuum using quantum field theory, we get values that are many orders of magnitude larger than what we observe. The observed value is not zero, but it is tiny compared to naive theoretical expectations. That mismatch is known as the cosmological constant problem. It is one of the sharpest examples of the universe feels too precise. If dark energy had been much larger and positive, the universe would have expanded so fast that matter would not have clumped into galaxies. If it had been large and negative, the universe might have recollapsed long before stars and planets had time to form. Instead, It has a value that allows billions of years of cosmic evolution, followed by a gentle but accelerating expansion that is only now becoming dominant. We know this value from several independent probes. The cosmic microwave background, or CMB, is the afterglow of the hot Big Bang, released when the universe was about 380,000 years old. Satellites like COBE, WMAP, and Planck have mapped its tiny temperature fluctuations across the sky. Those fluctuations encode information about the geometry and contents of the universe. When we fit the data with models that include dark matter, ordinary matter, radiation, and dark energy, we find that the best fit model has a dark energy density that matches what we infer from supernovae and from the clustering of galaxies. So this is not a single fragile measurement. It is a coherent picture. Dark matter is another key piece. We do not yet know what dark matter is made of, but we know how it behaves gravitationally. We know this from galaxy rotation curves, where stars in the outer regions of galaxies move faster than can be explained by the visible matter alone. We know it from gravitational lensing, where massive clusters of galaxies bend light from background galaxies more strongly than visible matter can account for. We know it from the pattern of temperature fluctuations in the CMB and from the way galaxies cluster on large scales. All of these point to a form of matter that interacts mainly through gravity, does not emit light, and makes up about 85% of the matter in the universe. The amount of dark matter and ordinary matter, and the way they interact with gravity, determine how structures grow over time. Tiny initial fluctuations in density, visible as temperature variations in the CMB at the level of 1 part in 100,000, grow under gravity into galaxies, clusters, and cosmic filaments. If gravity were significantly weaker, those fluctuations might not grow enough before dark energy takes over and accelerates the expansion. If gravity were significantly stronger, structures might collapse too quickly, forming mostly massive black holes rather than stable, long-lived stars. The balance we observe allows a rich hierarchy of structures: stars, galaxies, clusters, and the large-scale cosmic web. Spacetime itself is the arena in which all of this happens. In general relativity, mass and energy tell spacetime how to curve, and that curvature tells matter how to move. This is not just a slogan. It is a quantitative relationship encoded in Einstein's field equations. We test those equations in many regimes. In the solar system, we see the precession of Mercury's orbit, the bending of light by the sun, and time dilation in GPS satellites. In strong gravity regimes, we detect gravitational waves from merging black holes and neutron stars. On cosmological scales, we see the expansion and the way structures grow. All of these are consistent with general relativity, plus dark matter and dark energy, at least to the precision of current data. When I say the universe feels precise, I also mean that the initial conditions seem finely tuned. The early universe, as far as we can tell, was extremely smooth, with tiny fluctuations. The overall spatial curvature of the universe today is very close to zero, meaning it is nearly flat on the largest scales. We infer this from the angular size of features in the CMB and from other cosmological tests. If the universe had started with a slightly different density relative to the critical density, the curvature today would be noticeably positive or negative. In a positively curved universe with much higher density, the universe might have recollapsed quickly. In a negatively curved, low-density universe, expansion would be too fast for structure formation. Instead, we find ourselves in a universe that is close to spatially flat, with just the right mix of matter and dark energy to produce the cosmic web we observe. Inflation is one proposed explanation for this. Inflation is a period of very rapid, accelerated expansion in the early universe. It can take a wide range of initial conditions and drive the universe toward flatness and uniformity. Quantum fluctuations during inflation can then be stretched to cosmic scales, seeding the tiny density variations we see in the CMB. We have good evidence that something like inflation happened because the pattern of fluctuations in the CMB matches the predictions of simple inflationary models quite well, nearly scale invariant, Gaussian fluctuations with specific correlations. However, we do not yet know what physical field drove inflation or exactly how it ended. And inflation itself can raise new questions about fine-tuning, because the properties of the inflaton field, its potential, and its coupling to other fields must fall in certain ranges to produce a universe like ours. Let me connect these ideas to the fate of the universe, because that is where dark energy, dark matter, and gravity all come together. The long-term evolution of the universe depends on the total energy content and on how each component changes with expansion. Ordinary matter and dark matter dilute as the universe expands. Their density falls roughly as 1 over the volume. Radiation dilutes even faster because its energy is also redshifted. Dark energy, if it is a true cosmological constant, has a constant density per unit volume. As space expands, more space appears, and with it more dark energy, but the density stays the same. That means that even if dark energy was subdominant in the early universe, it eventually dominates as matter thins out. We see evidence that this transition is already underway. Observations suggest that the universe transitioned from decelerated expansion to accelerated expansion a few billion years ago. In a cosmological constant scenario, this acceleration will continue indefinitely. Galaxies that are not gravitationally bound to us will recede faster and faster. Beyond a certain distance, their light will never reach us. Over trillions of years, the observable universe from any given galaxy will shrink to a small island of bound structures. Star formation will slow down as gas is used up. Existing stars will age and die. White dwarfs, neutron stars, and black holes will dominate. On timescales far beyond current observation, black holes will slowly evaporate via Hawking radiation. The universe approaches a cold, dilute, dark state, sometimes called heat death. This fate depends sensitively on the properties of dark energy. If dark energy is not a constant but changes with time, the story could be different. If its density decreases, acceleration might slow or stop. If its density increases, or if its pressure is more negative than in the cosmological constant case, the expansion could accelerate so violently that all bound structures are torn apart in a big rip. Current data are consistent with a cosmological constant, but the error bars still allow small deviations. Measuring the equation of state of dark energy, the ratio of its pressure to its energy density, is one of the main goals of modern cosmology. We do this with supernovae, baryon acoustic oscillations in the galaxy distribution, weak gravitational lensing, and other probes. So far, the simplest model, a constant dark energy with equation of state W(-1), fits the data well. The fact that the long-term fate of everything depends on the exact value and behavior of dark energy is another way the universe feels precise. A slightly different value or time dependence could lead to a very different cosmic future. Yet we have no fundamental theory that predicts this value from first principles. In particle physics, we can explain many things by symmetry principles and deeper structures. In cosmology, when it comes to dark energy, we are still largely in the business of measuring and fitting. We should be careful, though, not to exaggerate the precision. Some so-called fine-tuning arguments are based on simple, often one-parameter variations, while in reality, many parameters could vary together. Also, our understanding of what counts as too precise depends on the underlying theory space we imagine. Without a complete theory of quantum gravity or a full theory of fundamental constants, we cannot say with certainty how surprising a given value is. What we can say is that, given our current theories, many of the numbers we measure sit in narrow bands that allow for a long-lived, structured universe. Take the density contrast in the early universe, the size of those initial fluctuations. If they were much smaller, gravity would struggle to grow them into galaxies before dark energy dominates. If they were much larger, the universe would be dominated by very dense structures and perhaps frequent black hole formation. The observed amplitude, around 10 to 5, is just right to produce the cosmic web we see. That is not proof of anything beyond physics as we know it. It is an observation that our universe's initial conditions are not random in a naive sense. They are highly ordered. Or consider the relative abundance of dark matter and ordinary matter. Dark matter drives structure formation efficiently because it does not feel radiation pressure. Ordinary matter, which interacts with radiation, is initially coupled to photons and cannot collapse as easily. Dark matter starts to clump first, forming gravitational wells. Later, ordinary matter falls into those wells and forms stars and galaxies. If there were no dark matter, structure formation in a radiation-filled early universe would be slower and might not reach the complexity we see today. If there were only dark matter and no ordinary matter, there would be no chemistry as we know it. Our measurements show a specific ratio, roughly 5 times more dark matter than ordinary matter. We do not yet know why that ratio has that particular value. How do we measure these ratios and parameters in practice? We use multiple independent methods. The CMB gives us a snapshot of the universe when it was young. The pattern of peaks in its power spectrum tells us about the densities of different components. Baryon acoustic oscillations, which are imprints of sound waves in the early plasma, leave a characteristic scale in the distribution of galaxies. That scale serves as a standard ruler for cosmic distances. Weak gravitational lensing, the subtle distortion of galaxy shapes by intervening mass, maps the distribution of dark matter. Galaxy surveys count how many galaxies of different masses exist at different epochs. Supernova surveys trace the expansion history. When all of these are combined, a consistent set of parameters emerges. That consistency is one of the strongest arguments that our basic cosmological model, called lambda CDM, is capturing something real about the universe. Lambda CDM is simple in form: a universe with cold dark matter, CDM, and a cosmological constant, lambda, governed by general relativity. It has only a handful of free parameters: the Hubble constant today, the densities of dark matter and baryons, the amplitude and slope of the initial fluctuations, and a few others. With those, it explains a vast range of data. That success is striking, but it also hides a deeper ignorance. We do not know what dark matter is. We do not know what dark energy is. We do not know why the cosmological constant is so small but not zero. We do not know why the initial conditions had the specific spectrum of fluctuations we observe. The model is precise and predictive, but its foundations are incomplete. When people say the universe feels too precise to be accidental, they often jump quickly to philosophical or metaphysical conclusions. As a scientist, I stay with what we can test. The precision we see is a clue. It suggests that there might be deeper principles, symmetries, or selection effects that we have not yet uncovered. It motivates theories like inflation, like certain models of quantum gravity, like attempts to explain the cosmological constant through new mechanisms. It also motivates careful observation, because small deviations from our current model could point the way to new physics. There are also tensions within our precise picture. One example is the current disagreement between different measurements of the Hubble constant, the current expansion rate of the universe. Measurements based on the CMB and the early universe give a value around 67 kilometers per second per megaparsec. Measurements based on local distance ladders using Cepheid variables and type Ia supernovae give a value around 73. The difference is larger than the quoted error bars. This could be due to unknown systematics in the data or analysis. Or it could be a hint that our model is missing something, perhaps in the dark energy sector or in the physics of the early universe. This is an active area of research. It shows that even in a universe that looks precise, our understanding is still evolving. Another open question is whether dark energy is truly constant. If it is a dynamic field, often called quintessence, it could roll slowly over cosmic time. That would change the expansion history in subtle ways. Future surveys, like those using large ground-based telescopes or space missions designed to measure weak lensing and supernovae, aim to constrain this. If we detect a deviation from W equals -1, even a small one, it would tell us that dark energy is not just a simple cosmological constant. It would open an entirely new window into fundamental physics. We also do not know if general relativity holds unmodified on the largest scales. Some alternative theories of gravity can mimic dark energy by changing how space-time responds to matter. We test these by comparing the growth rate of structures to the expansion rate. If gravity is modified, the relationship between how fast the universe expands and how fast galaxies cluster can change. So far, general relativity is holding up well, but the tests are still improving. On even more fundamental levels, we lack a complete theory that unifies quantum mechanics and gravity. Many proposals, like string theory or loop quantum gravity, attempt to do this. Some of these frameworks suggest that what we call fundamental constants might actually vary in different regions of a larger multiverse. In such scenarios, the values we observe could be selected by the requirement that structures like galaxies and long-lived stars can form. That is the anthropic idea. It is controversial because it is hard to test directly, but it is one possible way to interpret the apparent precision of our universe's parameters. From a strictly scientific point of view, it remains a hypothesis waiting for concrete predictions. In all of this, I want to keep the focus on what we actually know. We know that dark matter exists, at least as an effective description of extra-gravitating mass, because we see its effects on galaxy rotation, lensing, and structure formation. We know that dark energy, or something like it, exists because we see the expansion accelerating. We know that gravity is described extremely well by general relativity in many regimes. We know that the universe is expanding, that it was hotter and denser in the past, and that it has a finite age of about 13.8 billion years. We know that the universe is nearly spatially flat on large scales. We know the approximate fractions of dark energy, dark matter, and ordinary matter. Those are solid results based on multiple independent measurements. We also know that many of the key numbers in this picture, such as the dark energy density, the amplitude of primordial fluctuations, the ratio of dark matter to ordinary matter, and the overall flatness, appear to sit in ranges that allow a long-lived, structured universe. That observation is what people often translate into the intuition that the universe feels too precise. The precision is real in the sense that small changes in those parameters within our current models can produce universes with very different large-scale behavior. What remains unknown is why those numbers have the values they do. We do not yet have a deeper, predictive theory that takes in more fundamental principles and outputs the observed cosmological parameters. We do not yet know whether dark energy is truly a constant or a dynamic field. We do not yet know the particle nature of dark matter. We do not yet know the exact mechanism that produced the initial fluctuations and set their amplitude. We do not yet know whether the current acceleration will continue forever, or whether dark energy will evolve and change the fate of the universe. So when I say the universe feels too precise to be accidental, I am really saying that the cosmos confronts us with a set of finely balanced conditions that our current theories treat as inputs. They work extremely well to describe what we see. They do not yet explain themselves. The open scientific question is this: will a future deeper theory of space-time, gravity, and quantum fields show that these precise values are inevitable consequences of more fundamental principles? Or will they remain contingent features that we can only measure and never fully derive?